So yeah, welcome to our developers call for Ream Labs. So today's we're gonna start off with a study group session, and today I'll be talking about executing Ream's beacon state transition functions, and do it inside the zkVM. Um, okay, yeah. So three things I'm gonna talk about today. So first, I'll introduce you to the Ream state transition functions. Introduce you to the zkVM, which is ReZero for now that I'm trying out, and also I'll also demonstrate how the Ream STF or state transition functions is being run inside zkVM. And some disclaimers that the code that I'll be demonstrating today is only for prototyping purposes, not production, so it doesn't look as good as it should be. And also, we haven't tried anything live yet, so I've worked with test data from the consensus specs, but I think the test data is also pretty accurate representation of the actual consensus um, layer. So I think it should be nice as well. Also, I want to kind of like say thank you to the contributors to like all these like zkVM stuff on Ream, Junsong, Vid, and Paul, who have like contributed to all the like different repositories that we have for zkVMs, and also obviously like Ream contributors for building up the consensus specs into Ream. For stuff that I'm going to talk today, I'll go quickly. So first is the STFs inside Ream, what it looks like. I will explain how we are putting the STFs inside the zkVM, some of the early optimizations we have done, and also like some of the few next steps that we might be able to do after what we have done so far. Just to go through like the beacon state transition functions quickly. So basically, you guys are here. You probably know like Ethereum has like in the consensus layer, we are broken down into epochs. Each of the epochs have 32 slots, and these 32 slots usually it's filled by a block. But sometimes it's also some validator goes missing, it goes offline, or not proposed their block timely enough. So some blocks are missed. Right? But the important thing is that in one epoch there's 32 slots, and in these 32 slots, usually there would be like one block associated. But in some cases, blocks could be missing. So the slots numbers are always like running continuously. But for blocks, sometimes there could be like a block skip, so one slot might not have the block number associated with it. And if we look into the consensus specs, we'll notice that there are a few containers that are related to blocks. For example, like I took this example, beacon block and beacon block body. And so basically these like specs are turned into actual block that we see, for example, on beacon chain. And you can pretty much like see the similar kind of like data or information that you can see on beacon chain, which is actually kind of like representing the consensus, the blocks or the data inside the consensus specs. Two things that are important for this session is that you're aware that there's beacon block, and inside like beacon block you have the slots, proposer index, parent root, and so on, right? And you have the beacon block body, which contains like the actual substance of the block, and on the other hand, you have the beacon state. Right, so the block doesn't represent everything inside Ethereum or inside the consensus layer. There are some stuff that are existing beyond the blocks. For example, like if you see in the beacon states here, you can see the validators, you can see the balances. These don't change with the blocks. Right? Sometimes they get affected because of some like some validators are missing and stuff like that, but they are not really influenced by the blocks, so they stay inside the beacon state, right? And the main purpose of the state transition functions, I would say like there are two purposes. So the STFs first checks the validity of each block, right? So it checks that all the data that's proposed by a validator is correct, and if it's correct, then they would attest to it. The second thing is not just verifying the block and testing the block, they also have to apply the changes. For example, like if there's some, obviously like the slot has to change over time as block increases or slot increases and so on. Right, so the two main purposes of the SCF are to validate each block and apply the states. So that's the beacon chain in general, right? In terms of like state transition functions. Now I'm gonna get into what about like the state transition functions that we implement in Ream, right? And I think like it's pretty straightforward to study from. I think thanks to like our like modular code as well. I think like our code is like really great and really readable. So thanks to all the contributors there. But yeah, so in terms of like state transition functions, I think what we can look at is basically go into Ream repo, and actually probably the only file that you have to um, take note of is the beacon state file inside the consensus crate here. And what resides in this beacon state, first thing first is the state, obviously. So this is basically corresponds to the specs of Ethereum consensus specs. You see the same fields that you will see in the specs. And on the other hand, you also see the state transition function. And while the state transition function here looks pretty straightforward, I'll go into a bit more detail later on. But in terms of state transition function inside Ream, the only probably like two places that you have to be kind of like keep in mind of is the actual beacon state, which stores the data, and then there's a function called state transition, which is basically the beginning of all the state transition functions that need to happen in each of the block. Um, and next is if we look into the state transition function inside Ream repo, you'll notice that there are roughly three parts. So there's process slots. Inside process slots, there's also process epoch here on the right. And then there's also process block here. So these are kind of like the main three group of operations that happen when you transition a state from one block to another. Right, so process slots, and then in each of the slot, if the slot gets to the start of the epoch, then the process epoch gets run. Right, and then you can see that there's actually a lot of operations that happen both within the block here. So for example, process block does process the block header, withdrawals, process the execution payload, the random, sync aggregate, and so on. Right, and once every 32 slots, there's also extra processing that's done here within the epoch. Justification, finalization, inactivity, slashings, process pending deposits, slashing resets, effective balance updates, and so on. Right. So actually, it's a lot of information that the node or the validator has to process at any given slot, and especially during the beginning of the epoch, it also has to process a lot more operations to kind of like justify and finalize the epoch as well. So what basically state transition function does is it takes in the beacon state, right? And if you look closely at the state transition here, you can see the main two parameters here are the beacon state and the signed blocks. And what it outputs after going through all these like state transition functions is you get an updated beacon state, and you basically get a return saying okay, nothing failed, right? So if nothing fails and the beacon state updated, then you can basically rely on the updated beacon state that it's the state after applying all the process to the block that's just been received. But the problem is that you can see that there's a lot of operations going on. So the performance of the node and therefore the performance of the consensus layer is constrained by the node hardware that has to process all of these functions during a block, and also the block plus the epoch at the beginning of each epoch. So what that's the objective of like why the beam chain is looking into zkVMs, because we want to snarkify this entire state transition functions so that instead of like each of the node, whether you're a validator, you're a tester, or you're just like running a node to get the data out of the chain, you don't have to process all these operations and rebuilding the blocks one by one all the time, right? You are just basically relying on someone to generate you a proof that they have done all these processing, that they have got the updated beacon state out, and then nothing fails in there, right? And they supposed to generate a proof there that all of this has been done without any errors. So that's the purpose that we wanna do with Ream and the Beam chain. So that's a quick overview of the STFs and in Ream. Now I'm going to talk about like how do we put those STFs inside the zkVM. So now I'm gonna switch to consent zero, which is basically our repo for testing out bringing the Ream consensus crate inside the zkVM, and in this case, it's for zero. There are two things that you need to keep in mind for any kind of like CK program or zkVM program or project. And so basically for us here, the two folders that you have to kind of like put attention on is just the host folder and the guest. Right. So when we are running a zkVM program, there's actually two environments that we are interacting with. First is the host machine. The host machine is basically the machine that you are running, right? So it would be responsible for bootstrapping the project or the program. It would be receiving the data, for example, like the blocks or the states from the network. It would be processing all the insensitive or like all the data that you don't need to include as part of the proof can be processed there, and then send the information that need to be proven to the zkVM. Another thing is once the zkVM runs and gives you the proof, then the host machine takes the proof back and do whatever post processing that it needs to do. Right. For example, like it has to store the proof and most likely has to propagate the proof out to the network as well. Two things to keep in mind here is that we'll have to we need to consider that the host machine is untrusted because it's basically just Rust program and it's not part of the zkVM. So anything that gets generated as part of the host machine should be considered untrusted. Anyone can modify the data. And also another thing to note is it's capped by the physical machines or basically the machine that you are running by the performance of that machine, right? So it's pretty performant. On the other hand, on the guest machine, right, once it receives the data from the host, it would then process whatever the code that you run. You would put it inside the guest machine, and it would basically generate a trace and then generate and return the proof out back into the host. This part you can consider it as trusted because everything that gets run here is basically part of the proof. But the only downside is that it's capped by the zkVM performance, right? As far as I know, it's single-threaded, and also like because there's a lot of arithmetic operations happening behind the scene, performance inside the zkVM can be like really, really slow compared to the performance of the host. It's not like we can put everything inside the zkVM, right? So if we consider like all these state transition functions that are happening inside Ream or inside the beacon chain, if we are going to put everything, just basically this code inside the zkVM, it's probably going to take like forever to run. And we won't be able to complete it within 12 seconds or even like probably like 4 seconds that we need to process the block in order to participate in the network. So performance is very important here. Quick code walkthrough. So two things I want to show. It's basically from consent zero. The host, basically, so I'll show the host and the guest machine, right? So here, if you look here, this is the host program. So you can see that what I did is I included the Ream consensus and Ream libraries, basically like just simple like file operations here, and the actual beacon state gets included here. Some CLI stuff that I think you can basically skip, and then this is the main program. The actual code after all the bootstrapping, I think it happens around here. So we basically, because it's in the host, right, and we are actually using the full performance of our machine, we basically load the test data, download it from the consensus specs repo, and process it, right? And this is a pretty neat trick that Jin came up with. So basically, you take all the operations that happen, take all the test case, and then run each of the operation inside this repo. So we get a pretty convenient benchmark repo, benchmark code out of this. What it does, so for each of the test cases, right? So we have like attestations, attester slashing, and so on. It would basically like loop through and run each of them. For example, here it takes the file okay, input path, and then it basically fetch from the file the SSC that comes from the file. And what we do here is we for this example, we are just basically um, taking the SSC bytes and then just like basically chuck it into the zkVM itself. Right. So this is actually all pre-processing just to get the input in order to put it into the zkVM. We are not in the zkVM, right? But in most cases for a state transition, you basically need two things. So you would need a pre-state, which is basically the state before we are applying the block. For example, like block 0. And then we have the input, which is basically the input that's coming from, say, block 1, in order to process it and get a state 1 out of the next state out of it. So once we have the pre-state and input, then we start to build the executor environment, which is basically the zkVM environment here. What we do then is we just basically write, and this is basically the RISC-0 convention, that you write into the zkVM by building the environment, then basically write anything that you want to write in there. For example, here, I think, yeah, I write the length of the pre-state, also write the pre-state in, and also the input here. So the main thing that you have to see here is that the pre-state and the input gets sent into the zkVM, right? And once this executor environment gets built, then we basically start the prover by saying that, oh, this default prover should prove for the given executor environment, and using the ELF, which is basically kind of like the compiled guest program that it needs to prove against. So at this point, once this is called, we can then move on. Before we get back to here, we can move on to the guest program. Right, so if you can see here, you can see here that we are using a lot more of the Ream consensus code base. So most of the STF functions are here: attestation, tester slashing, and beacon block, and so on. What happens here is once we enter the zkVM, obviously we need to read out the stuff that we input, right? And this is basically reading out one by one in sequence. For example, we wrote down the length of the pre-state, and then the input. So it gets reflected here. So the pre-state length, the input, pre-state length, the pre-state, and then the input here. And once we loaded the input, then this is basically like pretty straightforward steps of the program, right? So we have the SSC bytes here. We deserialize the SSC bytes, and then we basically process that with the input. Once this is done, right? So once this is done, we basically get the tree hash tree root out of the pre-state, which is like the new pre-state, and then we basically commit this back. So this is the other important line. This is basically when we call the environment commit. This is basically what we are committing to. So basically, we are saying that after taking the state, the pre-state, and taking the input, after we process it, right, process attestation and so on, we get a new state root already. This has already been mutated. So we get the hash of the state, and then we commit it back that, oh, this has been successfully run, and the data that we get out is actually this state root, which is basically kind of basically the hash that confirms that the state is the state that we want. Once this gets committed back, then we are back into this stage where the prover, once it's done proving, we get the proof info. Just to kind of like jump towards like what exactly is the proof info. Oh, I am gonna jump here. So basically, this is from the RISC-0 zkVM. If you look here, the proof function returns a proof info. Right. So what's inside this proof? The proof basically has a receipt and a session stats. Right? Session stats, it's just the cycle counts. But the most important thing is the receipt here. And what's inside the receipt? There's a few things. You have the journal. So the journal is basically the public outputs, right? So for example, the state root that we just commented out would be part of the journal. Then you would also have the inner receipt. If you look at the inner receipt, you would see that it's an enum, and it's basically one of like succinct, groth, or even composite, or even like fake um, receipt here. So this is basically the whatever like smart construct that we config the with0 to prove against. And I think I'm not so sure metadata is probably I'm not so sure. I didn't look at this before, but yeah, some metadata here. Um, So knowing this, then we know that this proof info has the journal, which should contain the state root, and also like the proof that anyone else is able to use it to also prove that we have transitioned successfully and we got the state in return, right? So in this code, since it's because it's benchmarking, we also kind of like just basically take the receipt out from the proof info, and the way to do it is it's pretty easy. So we can just like basically take the receipt and verify it with the basically the ID of the consensus STF ELF file, and if because this is not failing, then we are sure that the receipt that we got and also the proof info that we got here is actually valid. So this is kind of like proving up to this point. Up to this point is all proving, and then this is the basically the verification part. So a lot of the heavy work should be done by the proving part already, and the receipt is basically you just have to have the right receipt and the right proof, and the verification should happen pretty quickly. Um, I think this is yeah. So this is basically the zkVM code in a nutshell. What basically we try to do is again like with it like it's this photo, right? So instead of like having all the nodes processing the slots, the blocks, the epochs, and so on, and every node has to do that. We basically saying that for the beam chain there should only well at least one honest person who's able to generate the proof in whatever start constructions, and then everyone else can actually take that proof, verify it against the same ELF file that gets compiled here, and then they should be able to rest assured that all of the basically that state root and all the information that the verifier has given is actually has been run against all these operations correctly. Up to this point, I'm not so sure. Does anyone has any questions before I continue? Right. Yeah. I think I was running this before. So yeah. So I'll just like let it keep running here. I'm not so sure. Maybe it's too small. It takes some time. So maybe one thing I can say is so basically I just like run attestation, but basically what this does is that it runs this part, right? It runs benchmark. Basically, if you are going to run it without the make file, you just run cargo release, and then instead of this parameter, you just send in attestation or attested slashing or whichever operation that you want to run. There are some excluded cases because I think they don't work yet because I think it works with like randomization. And basically what this script does is it scrapes out the logs and basically extract out useful information, for example, like the cycles and so on, into tables for us to process in terms of like the benchmark. Um, what you see in the logs, I don't think it shows in the log. I didn't output it, but basically, yeah, you can see it that once I run the zkVM, it outputs the logs here. Um, yeah, because I'm proving in dev mode. Otherwise, like it's gonna take a lot more time. We can see the cycles that it's taking here, and basically once it's done, it will also return the execution time here. I didn't tell it to output the receipt. Um, I'm not so sure if I can. Yeah, maybe I can try that later and show you guys. But yeah, it could take some time. Um, and yeah, so I think like in just like running, it's pretty straightforward. You just basically have to run the command. In case of like real world, you would probably have to get the code to extract the state from somewhere that you trust, and then retrieve the latest block, and basically run this by sending in the state and the block inside this program, and then it will generate the proof for you. On the verifier side, then you just basically need the proof, and then you can basically because in the proof you should also have the state root. Um, yeah, and basically with the state root, you are able to confirm that this is actually the state root, accurate state root that comes from the proof. Um, Yeah, so for the benchmark, it will just like keep running here for um, different scenarios that are in the test cases. Um, or actually, maybe I can try print out the receipt. No, but then yeah, it won't give you much information because then it's basically the the receipt here. Um, okay, then maybe I'll continue. Sorry, 30 minutes. Damn. I'll go a bit more quickly here. So early optimization. So we did some optimization so far. For example, like so in our first attempt, we basically deserialized the SSC inside the host and then pass in the basically Rust native structs inside the guest zkVM, right? So instead of that, we changed it to deserialize inside the guest. So for example, like here we on the left here we have the host. We basically just like send in the SSC bytes into the zkVM, and then here inside the zkVM we take the bytes and then we deserialize it out before we process them. This gave a pretty interesting, good result here. So before, when it was taking like probably like yeah around like 46 million cycles by just deserializing inside the guest, it's taking only like 18 million cycles. So that's like already like almost like 60% reduction in the cycles needed. Then we also did some partial beacon state. So basically, like before, you can see that we pass in the entire state. And the problem with that is that because the beacon state is really, really huge, if you look here, this is all the data is in the state, right? And not all of it is actually used all the time or for all the operations. So we basically like only take the fields that are actually needed for a sub operation and then pass it into the zkVM. So with this, for example, here we take the latest block header and the validator slash, and instead of like just passing the data in, the important thing is we also have to pass in the proof here. So for example, here we pass in the slot, and then we also have to pass in the proof here. What happens inside the guest is once it receives the slot, then it also has to verify that the proof is correct and that um, the this proof and the data that gets sent in is actually correspond to each other. With this partial beacon state update, I can't find the actual benchmark that I did, but I remember I mentioned somewhere that it's also another 60% reduction yeah, in cycles as well. So that's also another interesting thing that we did so far. And the third thing that we also did was using precompiles, and I think this is like a really quick win for any zkVM implementations. For example, here because like a lot of the stuff that we do, we are basically merkleizing a lot of stuff in order to get the state root. So instead of like using the native SHA-2 that comes, I think with another library, which is not a precompile, by just switching it to a precompile that was provided by RISC-0, that's a huge improvement as well. So that reduces the cycles down by 72% as well. So that's also a quick win for implementing zkVMs. So those are like the early optimizations so far. Some of the next steps that I can kind of like think of right now is first is benchmark Ream consensus again. But instead of doing with RISC-0, Jun also did with SP1. We could also do it with other zkVMs. Why? Basically because like all these zkVMs do have pretty bold claims. For example, CISC, they claim that they are already on 64-bit, while other zkVMs are on 32. So I think that would be interesting to benchmark. OpenVM, I think there's also a lot of complements there, and Pico and CK Engine, CK MIPS, and so on. Right, a lot of the zkVMs also try to be like the fastest prover, fastest verifier as well. But our use case, I think, is pretty heavy. So I think there's also pretty good benefit if we are able to benchmark one, if not all of them. And basically, by benchmarking, I think like there are two things to look out for. Basically, whether these zkVMs work out of the box with Ream consensus or not, and if not, what are the issues? And basically, the two things: the benchmark results, so that we can compare it with other zkVMs. Once the Beam specs comes out, then we can be confident earlier, with what kind of like zkVMs we wanna target to implement for the Ream client going forward. The second idea is 64-bit SSD libraries. This is still ongoing. It's quite a pain to fix so far, but basically, because most libraries use usize, um, but inside the zkVM, it's actually 32 bits, and then we have to do quite a few operations like SSC and macroization inside the zkVM, because these libraries use usize, so it's only like 30-bit long. So those lists that are beyond 32 bits are having issues with the usize inside the zkVM right now. So that's another area to tackle. And the third area is so this is from Justin Drake's direct like suggestion maybe a few like months ago. Why not try Poseidon 2 hash, which is basically I think the target like hashing algorithm that's going to replace SHA-2 for the beam chain, because it's a lot more efficient to operate on zkVMs. Paul already did a example of applying Poseidon 2 into the zkVM, but the results, I think, because it's like very prototyping code, it's returning probably somewhere around like 30 minutes per sub operations. While right now using SHA-2, we are able to do somewhere around like 6 seconds with the SHA-2 precompose. So that's a big difference. And yeah, with 32 minutes for sub operation, there's nowhere close that we can actually like apply Poseidon 2 into the beam chain with potentially like 12 seconds or even like shorter block times. So that's also another area that could be interesting. Yeah, I think that basically comes to the conclusion. If anyone else want to kind of like study more in details or contribute to the repos, these are the two main repos that we have: Consent 0 bench for V0, and then Consent SP1, us for SP1.